The question of how to form a best-fitting line has been around since the time of Descartes, when he first described coordinate space. Now, this question was answered by someone we met before, Carl Friedrich Gauss. You might remember Gauss from when I was introducing the normal distribution. Gauss, and also Pierre-Simon Laplace, were the first to describe mathematically the function of the normal distribution. Now, with regard to fitting a line, what Gauss described in 1794 was a method known as least squares. Now, if you're doing the math, 1794 places Gauss at the tender age of 17, when he solved a major problem in mathematics. If you ever want to feel bad about your accomplishments, simply read about the things that Gauss did when he was just a child. Now, it would be later on, in 1829, that he would work with Andrei Markov to develop the Gauss-Markov theorem. Now, these led to a development known as least squares and least squares regression. And this is simply an approach to fitting a model, or a line, to data where the sum of the square distances to the data is minimized. Now, this method gives us something very special. Least squares estimators give us unbiased estimators. That is, estimators that will not over or underestimate a population parameter on average. Now, it's beyond the scope of this course to talk about the mathematics behind least squares estimators, but let's look at two different regression lines and see how a least squares criterion would apply. So here are the data we have, and let's imagine two linear fits. Here's the first linear fit that I showed you before, and here are the residuals, the deviations between the points and the line. Now let's consider a second linear fit. So here's linear fit 2, so a different intercept and a different slope. And here are the residuals for this line, so the deviations between the points to this line. Now let's compare the two of these, linear fit 1 and linear fit 2. And remember, our least squares criterion says we want to minimize the sum of the square distances of the data, that is the points, to the line. Now here's how the linear least squares criterion looks if we write it out. Let's step through each component of this linear least squares criterion and see how our two models hold up. First, on the left-hand side, this is simply the equation for each line. Remember, the y hat I is the prediction for an individual, and our prediction for an individual is simply based on the intercept, b sub 0, plus the slope, b sub 1, multiplied by an individual's x score. The next part is the yi's. The yi's are simply the height on the y-axis for each individual. Notice that on the left and right side, we have the exact same yi's. People have their own final percentage score, and that has nothing to do with the line of fit. However, the y hat i's for each of these linear fits will be different. Let me show you those. Notice that the prediction for an individual is at the same location in x space, but is based on where the line is at that location in x space. So the y hat I is actually the location in y for each individual's predicted score. Let's take Tom here on the left. Tom, who studied 11 hours, had a predicted score just above what he actually got. On the right-hand side, this line made a vast underprediction for what Tom should have gotten on that exam. So notice that the y hat i's change between these two linear fits. And what we're doing with our linear least squares criterion is comparing an individual's actual y score to what is predicted for them. And we're trying to minimize the square of all of those deviations. So if we actually look at this component, the yi minus the y hat i's, the deviations or residuals in our model, what our linear least squares criterion is telling us is that we want a model that minimizes the squares of these deviations. So on the left, we can see that we'll have a much smaller sum of squared deviations than the linear fit on the right. So this linear least squares criterion actually asserts something relatively straightforward about what is the best fitting line. The best fitting line is simply the line that minimizes the sum of the squared residuals, or in other words, the line that gets closest to the points in squared space. Now, the linear least squares criterion has two important characteristics. As I said before, this will always produce unbiased estimators, that is, estimates of beta 0 and beta 1 that are on average correct. Second, and this was most important in Gauss's time, that it produces closed-form solutions. So by solving for the linear least squares criterion using calculus, we get simple equations that allow us to use sample data to form our estimates. That is, we have a simple formula for B0 and a simple formula for B1. Now, it's beyond the scope of this course to go over the actual hand calculations, but note that this was very important in Gauss's time. Gauss didn't have the benefit of using JMP to form these estimates.